Okay, we are now looking at Chapter 14. Chapter 14 says from randomness to probability because it comes after Chapter 13, which comes after Chapter 12, which comes after Chapter 11, and that would be dealing with sampling and randomness. And randomness to probability actually makes a lot of sense because probability is based off of random events. Alright, so we're talking about a random phenomenon. And it says it's a situation in which we know the outcomes could happen, but we don't know which particular outcome will or will not happen. And what we're talking about with that is when we think about randomness and we were sacrificing to the dragon, what we were saying is that any of the classroom could be selected to be sacrificed to the dragon, and that's fine. But what we also knew with that is that we had to know who could be selected. So when we talk about randomness, you have to have an idea, or you have to know what the population actually is that could be selected. But the randomness means that you don't know which one of those is going to be selected. And be careful with that because it doesn't mean that anything can happen. Certainly if I'm going to roll a die, and we're talking about randomness with rolling a die, I'm not going to roll a die and I'm going to sit there and say egg, because it makes absolutely no sense. So you have to have the known population. This is what could happen, this is what is going to happen. And probability based off of that is going to be determined as long-run relative frequency. Back in the days of the Titanic, we talked about relative frequency being the percentage of the whole. So it's based off of the whole, the known opportunities, and your probability is going to be based off that on the long term. It's the theoretical probability. And then what we have here is we have a statement here that for any random phenomena, each attempt or trial generates an outcome. So every time you do something, you get a response or a result, like a response variable. So that would be your outcome. Anytime that you do something that is a trial. On the next slide, we're going to actually see the word event too. And we're going to consider event and trial to be the same thing. And then you can see the rest of this. It's okay, you know, obviously stop and fill in notes as you need to go. But one thing we want to talk about is let's define probability in a more complete manner. We're going to say that probability is, as we try and write successful, oh, what the heck is that? That's crappy. All right, let's get rid of that. Let's start again. Probability is going to be defined in this class as success over opportunity. Opportunity meaning what can happen. Success is what you want to happen. By success, success doesn't necessarily mean it's a good thing. You could be talking about shooting baskets, and you could say, oh, the probability of missing, even though missing is not making a basket, that could be determined as success. So success is what you define it to be, what you're looking for out of what could happen. Alright, let's see if we can get back to the slides here. Oh, we got to get rid of this, and then we got to go back and do this again. This is going to happen all the time. Okay. Sometimes we're interested in combination of outcomes, such as a die is rolled and comes up even. So what that means is that you're talking about what's happening, and I want a very specific event. I want a 2, a 4, or a 6. And as we talk about that, the probability of that would be, well, there's 6 sides, and there are 3 possible successes. So we would have probability of getting an even number would be 3 out of 6. And here we've got the word event again, and we're going to consider event to be just like I roll the die, it's the trial, that's fine. But then when we start talking about combinations of events and outcomes are simplified if the individual trials are independent. What do we mean by independence? Wait for this. By independence, if we think back to looking at 2 variables with conditional distribution, when we were looking at that, what we would do is we would take a look at the conditional distribution of one and the conditional distribution of the other, thinking back to the Titanic. And when we were talking about that, we were talking about, does your position on the boat, meaning first class, second class, third class, or crew, influence whether or not you survive or you die? And we looked at those and said, are those 2 variables independent of each other? And we said they would be independent if those percentages were exactly the same. If those pie charts that we made were exactly the same. So when we had those pie charts, what we had is we would have a pie chart like this of first class, second class, third class, and crew, and these would be the survivors. And then we would have something like this, And this would be first class, second class, third class, and crew, and we would look at them and we'd say if the pie charts were exactly the same or if the percentages were exactly the same, then these two variables would be independent of each other. And this is really kind of like what we're looking at here with independence when we talk about probability as well. We're talking about, does one outcome influence the other? Think about rolling this die. If I talk about the probability of getting a 4, the probability of getting this 4 is 1 out of 6. 1 success out of 6s. And if I roll this die, I say, what's the probability of me getting this 4? It's 1 out of 6. Then I pick the die up and I roll it again. And I say, what's the probability on the second roll of me getting a 4? And regardless of what happened the first time, the probability of the second event is still 1 out of 4, 1 out of 6. So what that means is the probability of the second one is the same as the probability of the first one, meaning that they are independent of each other. The second roll is not influenced by the first roll. Okay? So let's break out the giant cards and let's talk about the probability of drawing a king. So we've got the giant cards. We're going to shuffle them. Here we go. Here's the shuffle. Wait for it. There we go. There's the shuffle. And we say, okay, what's the probability that you're going to pull a king? And there are 4 kings out of 52, so you go, oh, there we go, and we got a 4. So now, as I set this down, what's the probability of drawing a king now? And now the probability is 4 out of 51, and the probability has changed. And since they are not the same, what we could say is that the second event is dependent on what happened on the first event. So we can use that same thing that we had with the variables, sit there and say, if the probabilities are different, then the second event is going to be dependent on the first event. Can I make this, however, independent? And the answer is yes. If you put the card back. Okay, so I put the card back, and now they are dependent or independent, and we would say that these two are independent of each other, and that was called, if you remember right, with replacement, because I put that back. Okay. All right. Now, the law of large numbers. The law of large numbers says that the long-run relative frequency of repeated events is going to end up matching the theoretical probability. And they give an example here of flipping a coin many times. But let's talk about this in general. Would it be possible or likely for you to get 75% heads when flipping a coin? And let's say this coin is fair, and your thought is 75%? Probably not very likely. But if I said to you, what if you flipped it 4 times? 75% of 4 would give you 3 heads. And is that likely to happen? Your response is, well, yeah, actually, it's very likely that I could get that. So when I have 4 flips, that's fine. But let's flip it instead 20 times. And 75% of 20 would be 15. And are you as likely to get 15 heads as out of 20 as you are 3 out of 4? And the answer is no. You're probably not as likely to have that happen. And because it's less likely to happen, what that means is that as we add the number of flips, that probability is going to probably approach the actual theoretical probability. Now let's go to 100 flips. As I go to 100 flips, am I likely to get 75 heads? Not very likely. Okay? And if I go to 1,000, 750? No. And as I increase the number of flips, I'm going to have less likely chance of getting that obscure value, which means I'm going to be more likely to get closer and closer and closer, just to sheer numbers of getting the actual theoretical value, just due to sheer numbers. And that's what's called the law of large numbers. And as we go on, there's a misunderstanding of that, is that people tend to compensate for that. And we call that the law of averages, but the law of averages is wrong. It's not a law, it's not even a good idea. When you have 5 tails in a row, you flip a coin, you get 5 tails in a row, and people sit there and say, hey, I'm going to end up getting heads next time because it's due. And the answer is no, it's not due. Because the probability of flipping heads next time is 1 out of 2. And we're going to come right back after the break.